buffer solutions. A buffer solution resists changes in pH when a small acid or base is added to the solution. There are two types of buffer solutions: acidic buffer solutions and basic buffer solutions. For acidic buffer solution, pH will be less than 7. We're using weak acid, large weak acid, and large conjugate base of the weak acid. They have to be in ratio 1:1 for the maximum buffering capacity. We could use weak acid and strong base, but in ratio 2:1. Example would be a weak acid HF and its conjugate base F-, but we need a salt of F-, so we use sodium, in this case sodium fluoride. Basic buffer, pH greater than 7, lots of weak base, lots of conjugate acid, ratio 1:1, and we could use weak base and strong acid, ratio 2:1, because the half of the weak base will be reacting with the strong acid and then creating the buffer that we need. Example of the weak base is ammonia and the conjugate acid is ammonium ion. Maximum buffering capacity will be when the pH is equal to pKa. Buffer have a very narrow pH range of plus or minus 1. The pH scale is logarithmic of base 10. 10 times the conjugate base of pH goes up by 1. 10 times the weak acid, the pH goes down by 1. That's what the pH range is, plus or minus 1. And it goes down by a 10 times fold of 1. 100 times fold will be 2. It will go down by 2. 1,000 times fold will be going down by 3 or going up by 3. Here are some pKa values of weak acid. This one is monoprotic. HF is 3.2 and the range will be 2.2 and 4.2. If timefold applies, ethanoic acid 4.8. This one is diprotic, or you can call it polyprotic acid, and the pKa value is 6.4 and 10.3. The triprotic acid has 3 pKa values because it's got 3 hydrogens, so it dissociates 3 times. That dissociates twice, and that dissociates once, that dissociates once because it's got 1 H. 1 H here for that one. 2 H's, 3 H's. Polyprotic acid, like H2CO3, this is the polyprotic acid dissociating. The first dissociation, pKa1, H plus plus HCO3 minus. This is the conjugate base, and that will be the weak acid. It can also dissociate this way, forming water and CO2. This is happening inside the blood, this one here, and that too. Ka expression is concentration of H plus times concentration of HCO3 minus, the conjugate base, divided by the concentration of the weak acid. The pKa equals minus log base 10 Ka, and that equals 6.4. I can find the Ka value. That will be 10 to power minus 6.4. The blood pH is 7.4. If the pH goes below 6.8 or above 7.8, cells stop working and the person may die. Because it's diprotic acid, the second dissociation will be the conjugate base, now dissociating to H plus and CO3 2 minus. This is the second pKa, and we can write the Ka2 expression, which will be the H plus concentration times the carbonate concentration divided by the weak acid here, and that would be, this one is 10.3. I could find the Ka2 for this one, which is 10 to power minus 10.3. So the way the buffer works is if you add an acid, and this is the conjugate base of the weak acid, the conjugate base will, because it's got large quantity of these, will react with the acid added to then form the weak acid back and water, which is a new conjugate base. But if you have the base, OH minus, that will react with the acid and then form a conjugate base and water. Another example is a triprotic acid, and the first dissociation constant, the pKa is 2.1. The second dissociation is when the conjugate base here dissociates into new conjugate base with a phosphate buffer of 7.4. The third dissociation is when that dissociates finally to form the third pKa, which is 12.4. The phosphate buffer, this one here, the second one, is a very commonly used buffer in research labs.